Okay, this is the first lecture in Unit 6. It says sharing is caring. Sharing is sometimes more demanding than giving. So, the learning goals for this lecture is students will understand the nature of covalent bonds, and students will be able to distinguish between polar and nonpolar covalent bonds, and students will write the chemical formulas or name for covalent compounds. So when we're looking at this, what we should already know is that atoms can combine to form compounds. We looked at ionic compounds, and we know that they form between cations and anions and the transferring of electrons. And we know that the transfer of electrons is that ionic bond. Um, what we learned in the lab is that covalent compounds share electrons, and that covalent compounds do not conduct electricity, and covalent compounds have lower melting and boiling point than ionic compounds. They're relatively low. And then we have, looking at the octet rule, is that atoms are most stable with filled orbital shells. So they all want to have 8 valence electrons. That is the octet rule. And that elements with atomic numbers of 36 follow the octet rule, except for those hydrogen and helium. Those guys, they only need 2. Now, sharing electrons. Sharing electrons can help atoms satisfy the octet rule. So when we're looking at ionic compounds, they transfer electrons to satisfy the octet rule. Well, ionic or covalent compounds, they can share electrons, and each atom thinks that it has the shared electron. So it thinks that it has it, and it's sharing it, and so therefore it satisfies it. So if we're looking at this, when we put all these hydrogens around this carbon, well, each hydrogen will bring 1 electron. So there's that hydrogen atom, there's that hydrogen atom, and there's that hydrogen atom. And there's that hydrogen atom. Now, carbon brings 4 electrons. 1, 2, 3, 4. Now, when they share, hydrogen only needs 1 more. So guess what? It thinks it has 2. It's happy. Each hydrogen does that. It thinks that it has 2. So each one of those guys are fine. Then the carbon, if we look at the carbon thinks that it has 8. So it's going to satisfy the octet rule. So covalent bonds, ionic bonds form when electrons are removed or added to an atom. A covalent bond forms when we just have the sharing, when they think that they have that atom. Now, electronegativity. When we look at electronegativity is the pull or the measure of an atom's ability to capture an electron. That it depends on the outer or the valence electrons and the distance from the nucleus and the number of protons and the stability of the ion. We need to know that electronegativity increases to fluorine. So it's going to go from the bottom left to the top right of the periodic table towards fluorine, and fluorine is the most electronegative. So when we're looking at the electronegativity trend, we see that it decreases as you move down the periodic table. So it decreases this way, so obviously it increases going up, and then it increases as you move across the periodic table. So it increases this way. And it excludes the noble gas. So everything is going, the electronegativity is going to increase towards fluorine. And why is this important? Well, it's important in covalent bonds because it depends on who kind of hogs the electrons. So a covalent bond occurs between 2 nonmetals. And so when we're looking at the periodic table, we would say that they occur between, and here's our stair step, and it occurs between 2 things on the right side of the periodic table. It occurs between 2 nonmetals, and that molecules have a defined shape. So our molecule is going to have a very specific shape. They are gases or liquid at room temperatures. They have very low melting points and very low boiling points. They don't have really strong intermolecular forces. They don't have a lot of things holding molecules close to each other. So looking at this, it says draw what happens to electrons in a covalent bond between two chlorine molecules. So when we're looking at this, and we see that this is a Lewis structure, which we learned back in Unit 5, and we see that when they bond so that they share. And so what they're going to do is we can see that this chlorine has 1, 2, 3, 4, 5, 6, 7. So it only needs to share 1 to get 8. So when we're looking at this, you can kind of think that these two guys will kind of go in the same spot and share with each other. So when we're looking at it, we can say that we have chlorine and a chlorine, and then we go 1, 2, 3, 4, 5, and we go 6 and 7. And then this chlorine will go 1, 2, 3, 4 and share it right there. 5, 6, 7. And so if we're looking at it, this chlorine right here thinks that it has 8, and this chlorine right here thinks that it has 8, and so therefore it forms a covalent bond. Looking at the next one, it says covalent compounds have a much lower melting point than ionic compounds. Using the idea that opposites attract, and that's really Coulomb's law, explain why. Well, remember, in ionic compounds, we have a transferring. We have a positive and a negative. We have a cation and an anion. In a covalent compound, really what we have is we have a sharing. And so we don't have this big positive and negative, so they don't all line up in a nice, neat pattern like the ionic compounds do. So they don't line up with every positive is surrounded by a negative, and every negative is surrounded by a positive. And so it doesn't line up that way, and so they don't kind of hold each other together, and so that's why they have really low melting points. Now, sharing equally. Electrons can be shared equally between two atoms. They can be. They don't tend to be, though, because not everything really shares equally. But if they do share equally, we call this a non-polar covalent bond. Atoms have the same electronegativity. So when we were looking at those two chlorines, if we think about it, they have the same exact electronegativity because guess what? They're the same. And so in a non-polar bond, the shared electrons, so these guys in the middle right here, those electrons are pulled equally in both directions. And what we can say is they have an electronegativity difference of less than 0.4, which is extremely low. The one thing we need to understand is if it's bonded to itself, the difference in electronegativity, difference means subtract. So even if this was 3.6 and this was 3.6, 3.6 minus 3.6 is 0. So therefore, it's going to be non-polar. Main thing we want to know, if it's bonded to itself, it's non-polar. Generally, everything else is going to be unequal sharing. So, sharing unequally, not all the electrons are equally shared between the atoms. The shared electrons gravitate towards one atom or another. And so when we're looking at this, we call this polar covalent. So polar meaning that it has a pole. So oxygen has a higher electronegativity value. Hydrogen has a lower electronegativity value. And so what we see is the electrons that are shared are pulled towards that oxygen, and it makes it polar, where we have a negative pole here and a positive pole there. It's polar. And that's where usually we have a difference in electronegativity that is going to be right in between 2 and 0.4. So we can actually look up their numbers on the periodic table and subtract them, and that will give us the difference in electronegativity. And if it's between 2 and 0.4, then it's going to be polar covalent bonds. So looking at this, it says the carbon-hydrogen bond is the basis of life as we know it. Describe the type of bond formed between a carbon and hydrogen using your periodic table of electronegativities. So when we're looking at this, when we're looking at that carbon-hydrogen bond, if we look at carbon, carbon's going to have about a 2.5. And hydrogen's going to have a 2.1. So the difference in those, 2.5 minus 2.1, is going to give us something right around 0.4. And since it's right around 0.4, what we can say is that difference in electronegativity is going to give us a nonpolar covalent bond. And so that's going to give us, because basically they're really close in electronegativities, they're going to be nonpolar. They're going to share equally. Looking at our next one, it says using Coulomb's law, compare the properties listed below for polar covalent compounds versus non-polar covalent compounds. So when we're looking at this, polar versus non-polar. Now remember, ionic compounds, they have a positive and they have negatives, big time positive, big time negatives. And so remember, they have high boiling points. They conduct electricity in high melting points. Well, a polar covalent is going to share some of those properties. It's kind of like that. Since they're polar, since they kind of have a little bit of a positive and a little bit of a negative, they're going to have a higher boiling point than nonpolar. They're going to conduct electricity more than nonpolar, and they're going to have higher melting points than nonpolar, because that's what polar means. It has a positive and negative, and anytime we have positive and negatives, we're going to have that opposite attracts, and that's going to give us a little higher boiling, conducting, and melting. They're extremely low compared to ionic compounds, because ionic compounds are really big positives and really big negatives. But compared to nonpolar, nonpolar is basically nothing. Okay, it's really low. And then polar is just a little bit above that, and then ionic is way above both of them. So a mastery level question. It says the molecule for CH4 forms this tetrahedral shape as shown. Determine whether the molecule as a whole is polar or nonpolar using your periodic table with electronegativity. When we're looking at this, since they're all carbon-hydrogen bonds, and we know that carbon-hydrogen bond is going to be nonpolar, then that whole molecule as a whole is going to be nonpolar. Jumping to naming. Now naming, this is a lot easier to name than ionic compounds. The one thing you have to do is you have to memorize the prefixes. You have to memorize mono, di, tri, tetra, penta, hexa, hepta, octa, nana, deca. You either have to memorize them, or your teacher might give them to you on a formula chart. But we need to have those. So the way we name covalent compounds is we identify the first element in the compound, and we move left to right across the periodic table. Hydrogen is hydrogen in between nitrogen and oxygen. So when we're looking at this, we determine the prefix that is necessary. We identify the second element. So when we're looking at this, the first element, when we're looking at it, we move from left to right. So we're starting with left, going to right. Whatever we hit first, that's going to be our first element. We put hydrogen in between nitrogen and oxygen on where it goes on the compound. And we determine if a prefix is necessary. On the first one, a prefix is only necessary if it's 2 or up. We identify the second element, and that's moving from left to right across the period. And we determine if a prefix is necessary. On the second one, a prefix is always necessary. And then we replace the ending of the second element with IDE. A lot of words. It's really simple once we get to it. The big part, making sure we know our prefixes. So when we look at this, it says write the chemical formula for dinitrogen pentoxide. So when we're looking at this, di, if we look on our list here, di means how many? Well, it means 2. So dinitrogen means 2 nitrogens, so N2. Pentoxide, pent is 5, so we go O5. Really simple, right? Carbon tetrachloride. Carbon, we don't need a prefix on carbon, because guess what? There's only one. So C, tetra means 4, so Cl4, chloride. Jumping on, let's name the following covalent compounds. So we're looking at this. How many hydrogens do we have? 2. So dihydrogen. And how many oxygens do we have? 1. So we put monoxide. Looking at this one, how many carbons do we have? 1. Now the only trick, remember, we don't need to put monocarbon, we just put carbon. We don't need to only need to put a prefix on the first one if there's more than one. carbon. How many oxygens do we have? One. We always put a prefix on the second one, so it's monoxide. And then lastly, we have phosphorus. We don't need to put mon because we don't put it for the first one. If it was two, we would put di, but remember, it's just two and up. And then chloride for chlorine. And how many do we have? 5. So it wouldn't just be chlorine or chloride, it would be pentachloride. So phosphorus pentachloride. And that's how we name our covalent compounds. So the last thing we're going to talk about is just looking at metallic bonding. Kind of a little, it's like covalent bonding in the fact of there are sharing of electrons, but it's a very special type of sharing. What we call these electrons are delocalized, and I want you to write a key phrase down here. This is C of electrons. And so what we're thinking is all of these electrons, they really don't belong to anybody. They kind of just flow throughout the metal. And so we say that they're in a sea of electrons, and they're just kind of flowing throughout. They're shared between everybody. There's not really belong to any one particular thing. So when we look at metallic bonding properties, they have delocalized electrons. What that allows to do is the free movement of electrons. So basically, metals conduct electricity because guess what? Metals really don't hold on to their electrons. They share them with everybody. They share it with all the other atoms in the metal. We have the transferring of energy via electrons, meaning metals can heat up. So they can conduct electricity. They can heat up really easily because all these electrons are shared between all of them. And it's different than covalent because they're just kind of everywhere. Just everybody can take everybody electrons and they don't really belong to anything. And then metal ions can slide past each other in a sea of electron. So that's why we're able to, they're very malleable. We can pound them in the sheets or put them into wires, is because they can kind of flow around each other. And you can kind of think of these electrons kind of flowing and sharing in a sea of electrons. Different than covalent, because covalent, they're actually stuck in that bond. Metals, metallic bondings, they just flow really easily. So an example, it says using the description of metallic bonding, explain why solid metallic bonds can change shape easily or easier than a solid ionic compound. So when we're looking at these, those delocalized electrons allow for free movement of positive ions through the sea of electrons. So it allows it to flow because of the sea of electrons and allows it to flow past everything.